My name is This I will explain how graph algorithms are used in real life, specifically in route planning and transportation networks. Every day, we use applications like Google Maps to find the fastest route between locations. These applications rely on graph theory and efficient algorithms to solve to solve complex problems quickly. One of the most important algorithms used for this purpose is the Dijkstra algorithm, which helps us find the shortest path between locations. To understand how this algorithm works, let's start with a simple scenario. Let's imagine that we have a variety of different towns scattered in different locations. Some of those towns are connected to other towns with roads, such that we could travel along the road to go from one town to another. Not all roads have the same travel time though. One road might take 3 minutes to travel through, while another might take four. And our question is this: what's the fastest way to get from town A to town B? This is a specific example of a more general problem in graph theory, where we have vertices, in this case our towns, that are connected by edges, in this case our roads. Together, the vertices and edges form a graph, and, and in a particular, this graph is a weighted graph because each edge has some value or weight to indicate how costly it is to travel along that edge, measured in either distance or time. And with this graph, we'd like to determine the shortest path from one vertex to another. So how does Dijkstra algorithm allow us to do this? Ultimately, we need to figure out how many minutes it will take to get to town B. In doing so, though, it might be useful to figure out how many minutes it would take to get to the other towns too. So ideally, we want to label we want to label each town with a number representing the shortest time required to get there. But of course, we don't know that information yet. So instead, we will label each town with the shortest time we found so far to get to that town. Before we started the algorithm, we don't have any known way of getting to the towns, so we labeled them all with infinity. The only town that we can label correctly is our source, town A, which we can easily label. We are we are getting we are starting there, so it takes zero 0 minutes to get to this town. Once we have found the shortest path to a town, let's call that town explored. For all other towns, we'll consider them unexplored. We don't yet know what the shortest path to them is. So, what can we do next? Dyke, Dyke's, Dijkstra algorithm repeats a two-step process. First, we update our estimates, and second, we choose the next vertex to explore. So let's start with the first step, updating our estimate. We know we can get to town A in 0 minutes, and because we can get from town A to town C in 3 minutes, we know we can get to town C in 3 minutes. That's much better than our current estimate of infinity. So we will update our estimate to be 3, and we can do something similar for town F. We can get there in 2 minutes. So we will update our estimate after we have considered all possible roads connected to town A. We are done with this step, and now the next step is choosing which town to explore next. And the rule is quite simple. The town we explore will always be the unexplored town with the smallest estimate. In other words, the next town we explore should be among all of the unexplored towns. The one we know we can get to the quickest, in this case, that's town F, which we can get to N in 2 minutes. And now, the two-part process of Dijkstra algorithm repeats. We first update our estimates by looking at the towns connected to town F. It takes 5 minutes to get from town F to town G. So if we can get to town F in 2 minutes, then we can get to town G in 7 minutes. The sum of those two values. Likewise, we can get to town B in 8 minutes, and we get to town E in 5 minutes. We can also get to town C in 4 minutes. 2 minutes to go from A to F, and then another 2 to go from F to C. But 4 minutes is actually more than our current best estimate for town C, which is 3 minutes. So we don't want to update anything here. Remember, for each town, we want to store our best estimate for the shortest amount of time required to get there. So let's keep going. The second part of Dijkstra tells us to explore the unexplored town with the smallest value, and in this case, that's town C, which we can get to in just 3 minutes. And the process repeats again. Going through town C, we can get to town D in 7 minutes, and we can also get to town E in 4 minutes. 3 minutes to town C, plus 1 minute from C to E. That 4-minute estimate is better than our current estimate of 5 minutes. So we will update our estimate for town E from 5 to 4. The next town to explore is town E. Among all the unexplored towns, it has the smallest value noticed. Notice that each time we explore a new town, it's guaranteed that we will have found the shortest path to get to that town. Since if there were some shorter path, we would have explored that shorter path first, because we prioritized exploring the smaller values. And through town E, we can get to town B in just 6 minutes. 4 minutes to town E plus 2 minutes to go from E to B. So we update our estimate for town B to be 6, which is better than the previous estimate of 8. And now the next town to visit is town B, our destination, and that tells us that the shortest time needed to get from town A to town B is therefore 6 minutes, and that's Dijkstra algorithm for finding the shortest path in a graph. Now, there are a few things worth pointing out here. The first is that technically our algorithm has only given us how long it will take to get from town A to town B, and hasn't actually given us which path to follow. In order, uh, uh, in order, in order to actually reconstruct that path, we will need to add a step to our algorithm. Every time we update our estimate for a town, we should also keep track of what previous town we visited in order to get to this new estimate. If we keep track of that for each of the towns as we progress through the algorithm, then at the end we can figure out what the best path is just by what the best path is just by following those arrows backwards to the beginning. Also, it's worth noting that this algorithm only works correctly if the weight of all of the edges are non-negative, since otherwise some negative length path might result in a shortest path that our algorithm wouldn't be able to find. Another thing we're thinking about is how we efficiently determine which unexplored town to visit next. We want to always pick the unexplored town with the current smallest estimate. So some kind of priority queue that give us efficient access to the next town. To visit can make our algorithm faster. And that's a Dijkstra algorithm for finding the shortest graph. We keep track of a distance and a previous town for each vertex. The distance for all vertices starts at infinity, except for the source, which starts at 0. And then, as long as we haven't explored the destination yet, we picked the unexplored vertex with the smallest distance. To explore next, we consider all edges connected to that vertex, and if we can come up with a shorter path to a neighboring vertex, then we will update our distance estimate and remember which town uh, we came from. We came from. Once we have explored the destination, we have our answer. We know how quickly we can get to the destination, as well as what the shortest path actually